All right. Welcome, everybody. My name is Robert Kovacs from the MÁ~iller Institute. I'm a PhD student there with Professor Patrick Baudisch. And I'm going to present you TrussFab, which is a system for fabricating large-scale objects which can hold a human weight. Okay, but to start from the beginning, traditionally, personal fabrication has been used for creating hand-sized objects because the underlying technology doesn't care very well, while large-scale fabrication is still the privilege of industry. So there is the obvious problem that the print volume doesn't scale very well because the printing machine has to enclose the printed object all the time. So researchers and makers came up with several solutions for that. For example, embedding ready-made objects into the design, and that helps fabricating larger objects. But the main challenge, what we have to consider when fabricating large objects, is to withstand large forces. And that's because of two reasons. First of all, large objects has to hold larger weight, for example, a human. And second of all, large objects involve larger levers, and levers are scaling the forces cubed, so 10 times longer lever can make the force 1,000 times longer, and altogether that can lead to 100,000 larger forces. And to design these structures, that requires substantial engineering skill. So that's why we created TrussFab, which is a fabrication system for creating large sturdy objects that embodies the required engineering knowledge. So let me show you the workflow, how it goes. This is the design environment, which is running inside SketchUp, and there is a toolbar, and users can design their objects using the regular SketchUp tools, and later convert it to a rigid mesh structure. Or alternatively, user can design from scratch using our TrussFab tools to create these objects. And I will tell about these structures later, what is the key behind. When we are satisfied with our design, the software also runs structural analysis, so we can be sure that the structure can hold up the desired weight. And at the end, when we are done with the design, with the Fabricate button, we export the hubs. So these are the 3D printed pieces which are holding the bottles together. And following the imprinted IDs, user can assemble the design. Okay, but let me talk about these special structures, because that's the key behind. First of all, TrussFab uses bottles not as big bricks by stacking them together, but as beams in a particular arrangement. So if you look at this chair, it only has triangles, and that's the key, because to explain this, I will use the example of a tetrahedra. Here, if we step on this tetrahedra, the vertical bottles are clearly useful because these are holding up the person's weight. But what about the bottom ones? So if we would not have the bottom ones, these long levers would amplify the forces, and it would break very easily. You can see that clearly. But if we add these bottom connections, then those are closing the triangles and prevents this sliding apart. And there, as a result, no bending moments are at the top hub present. So there are only compression forces on the vertical ones and tension on the bottom ones. And this is exactly the definition of a truss. A truss is a system system where only compression and tension forces are present. So as a consequence, TrussFab affords building trusses. And it does that by offering primitives, which are miniature trusses, like the tetrahedra and the octahedra. And second, it's allows stacking them together by their triangular surfaces. And as a consequence, everything what we create with TrussFab remains a truss. So this is the editor, and this is how we design the chair. First placing an octahedra and attaching two tetrahedra to it to form the backrest. And to allow more flexibility to this, user can adjust their structures by elongating certain edges, by combining different bottle lengths, 1/2 liter, 1 liter. And so this allows us to adjust, for example, the backrest of the chair. And to have even more expressiveness, not to have just these discrete lengths, software can also elongate the connector pieces and achieve all the in-between sizes. And at the end, user places the pots and the seating surface, and here we have the functional chair. And if we are satisfied with our design, then we go to the load testing, which is a two-step process. First, we place the virtual load on the node points where the load will be present, and then we run the structural analysis, which calculates the forces inside the members and colorize the bottles so we can see which is loaded on compression and tension. And here there are no warnings. If we would put too much load on our structure, like 200 kilograms on this tetrahedra, then the exclamation mark shows us that this is overloaded. And I will tell you how we got these values to make sure that the bottles can withstand the desired force. But in our case, this chair looks good, and we can safely sit on it. Okay, so this is the key idea behind the editor, and I will show you how to create larger structures efficiently. If we are creating a pavilion, we can use the beam and block tool to create a big piece of a truss in one go. Then we don't have to assemble them from tetrahedra and octahedra primitives. But this looks still very edgy and rectangular, so to deform these structures, we use the freeform tool, which can drag on any point of the structure, and the software will align the rest by running dynamic relaxation algorithm. And if we go even larger, the system also supports hierarchical constructions, which is a very general thing in architecture to practice. First, users create the strong outlines, the supporting beams of the structure, and later, to cover the surfaces, they apply the flat fill tool to create only a two-dimensional single-layer cover for the structure, which saves us lots of bottles and can be fabricated also much faster. And I will show you also that how. Okay, and this facade tool was also, we explored different usage for structures which are self-holding, so we don't need any structural support for them. They are held up only by their curvature. Okay, so that's all about the software. Let's look at what's happening under the hub, how we create these mechanical components, the members and the hubs. The function of the hubs is to hold the bottles together. That's simple. So our first, most intuitive design was to create threaded connectors where we screw the bottles in them, and that's it. We thought that we are ready, except that it was not that easy. When we started to connect, to assemble our first triangle, which is a closed loop, we ran into an issue that when we were screwing in the last one, we were always unscrewing the other side of the bottle, so we couldn't assemble a single triangle. For that reason, we designed a second type of connections which slides into the bottle. This we call the snap connector, and this allows free rotation. And then the software arranges them in an alternating manner on the hubs, so resolving the screwing direction issue. Okay, but if you have seen the pavilion upstairs, you might have noticed that we used a slightly different hub design. And that's because we try to optimize it for speed and strength. So these hubs only have a generic flange on the side, on the ends, and a separate piece, a C-cuff. It connects the bottles to the hubs by holding them to the flange. And the main benefit of this design is that it's particularly good for printing on an FDM printer, where the printing direction matters a lot, and it can be sliced always in the best possible direction. And I mentioned the 2D single-layer truss covers, and for that we designed another type of connectors which can be produced on a laser cutter approximately 40 times faster, and it saves us a lot of time and material too. Okay, and you probably were wondering, how do we connect these bottles by their bottoms? So most typically we use a double-sided screw and just screw them together, or maybe even easier, we use an extra long screwdriver and screw a simple wood screw into them. The downside of this is that it actually destroys a bottle, so we cannot reuse them. And for that, we also explored a couple of non-destructive connectors, like taping them together or with rope or putting a shrinking tube around them. And the benefit of this is that bottles are intact, and maybe they can be even inflated to increase the structural stability. Okay, and speaking of stability, we also validated our design. We brought these hubs and members to the technical university, to the mechanical engineering department, and put them into this mechanical torturing machine, which was applying force, pulling and pushing force until they broke. And while doing that, it recorded us these diagrams where on the vertical axis you see the applied force, and on the horizontal axis you see the deformation. And from these diagrams we can read the point where they actually broke, and we collected this data into a table. And we saw that on compression forces, the connector pieces were basically not breaking at all, but the bottles were buckling at around 85 kilograms. And on tension, the most critical point was the threaded connector, which was ripping off at 135 kilograms. And these are actually the values that we fed into the software to warn the users if they are exceeding the limits of of these parts. But of course, bottles vary across the world. There are many different types. The good thing about them is that the bottleneck is actually standardized, but the strength and the structural stability is not very standard. So we would encourage everybody before using them for creating their structures to validate the strength of this. And as a future step, we also would consider dynamic forces to make sure that the structures can withstand shocks, wind, and vibration forces, which is currently not the case. We consider that the loads are static. Okay, and the implementation is fairly simple. Our TrussFab toolbar lives inside the SketchUp environment as a plugin. It's coded in Ruby, and it uses a couple of external tools, like for the finite element analysis, we use Karamba 3D, and to generate the hubs, the 3D models, we use OpenSCAD. And we are thinking about to share this software because we get so much interest and great feedback. And with this, I would like to conclude the talk. TrussFab is a design tool for creating large, sturdy structures that embodies the required engineering knowledge, and it affords creating truss structures made from bottles and 3D printed connectors, which can be fabricated on a desktop printer. And I would like to thank to all of my co-authors who did a great job on this work, and this was a big team effort. They were mostly working on the software side, but to bring this demo to Kai, we had the whole lab working on the project, preparing the 3D printed hubs and the bottles. Also, it was a big effort to bring all this to Kai. Thanks to Alex and Patrick for supporting that. Thanks for Lisa Suan for this spectacular pavilion design, and all the SVs who helped assembling this yesterday. It was amazing. Thank you.
Yeah, thank you for the nice presentation. I really enjoyed the size and scale and making us think bigger. My question, there are two questions here. One is most of your strength evaluation were mainly on tension and compression, but as you know, a lot of these structures buckle, including bottles or cans. If you stand on them and you just tip it, just crumbles off. And secondly, you also use 3D printing for connectors. I would like your comments on fatigue issues there, especially with those hinges. I've noticed that if you repeatedly pull it back and forth, they tend to break. So although your strength evaluation and static would have worked well, what are your comments on your future in terms of more dynamic properties? Would you pursue the same direction or would you change?
So, yeah, that's true that the printing direction was a big problem, and that's why we switched to these other cuff types. If we would print everything on the SLA printers, then it would already be resolved. And yeah, but the software should also consider the dynamic forces, but that's a separate, larger issue to address.
Hey, Dan Ashbrook, Rochester Institute of Technology. I have two questions. One is whether you've considered the ability to use other materials besides just bottles, because bottles are, of course, everywhere, but there's lots of other stuff that we could recycle as well.
Yes, absolutely. That's I didn't mention because of time, but we considered using, and we can use basically any other long-shaped object. We did the first experiments with pencils and chopsticks, but we could use also something larger like broomsticks, or I heard about comments that we could use also even ski blades.
Cool. So then my other question is, a bottle seems to be much more robust if you have a cap on it, because then you have the air inside.
Yes.
Not as compressible. Did you look into keeping caps on, filling the fluids?
Yes, so some of the chairs upstairs are actually fabricated like that, which the downside is that then we cannot use the screw connection, but we have to tape them together, but then we filled up in compressed air, and then they are much stronger. So we can use weaker bottles for the similar, and get similar results.
Cool. Thanks, really great work.
Hello, Laura Olberg from the University of Calgary. It's less of a question and more of a suggestion. I would be fascinated to see what happens if you combine this with some of the work from SIGGRAPH that's looked at how do you cover these sorts of structures. Since the application domain I immediately see are things like doing refugee housing or short-term really quick builds that you need to do. But thinking about not just the structure but also the skin that you would put on top could be a really cool extension for this.
Yes, I think that would be a really good future extension of the project. Yeah, so far we only had these cover plates, what you can use. We use it mostly for the chairs and the tables, but a more organic shape would be very cool.
Thank you, Robert. I have a quick question. You presented non-destructive connectors. Did you also test them? If so, were they as stable as the nailed one you demoed in the pavilion?
No, when we did the force testing, we only tested the standard general German refillable bottles, but we do not have the time to test all the other possibilities. But yes, that would be certainly a point to do in the future.
Thank you. The last talk